Okay, cool. Thank you. Okay, so it is my pleasure to introduce our next speakers. They are Alan Kuntz, that is here in place of Tucker Hermans, and Isabella Huang. And they are from the University of Utah and University of California. In particular, Alan is an assistant professor in the School of Computing and Robotics Center at the University of Utah, where he leads the Artificial Intelligence and Robotics in Medicine Lab. Prior to joining as faculty in Utah, he was a postdoctoral scholar in Vanderbilt Institute for Surgery and Engineering and the Department of Mechanical Engineering at Vanderbilt University. And he completed his PhD in computer science at the University of North Carolina at Chapel Hill. While Isabella is a PhD candidate whose research focuses on modeling and control with soft materials in robotics, she is advised by Rosina Baishi at the University of California, Berkeley, where she develops soft tactile sensors for use in physical human-robot interaction. She is also a collaborator with the NVIDIA Seattle Robotics Lab, working on simulating and predicting the physics of grasp planning for deformable objects. And prior to graduate studies, Isabella completed her undergraduate degree at the University of Toronto in 2017. So thanks again for being here, and the floor is yours.
Thanks, Martina. Good afternoon, everyone. I'm really happy to be here along with Alan to present our work today. And before I begin, I just want to acknowledge all our collaborators without whom this would not be possible. Okay, so in this talk, we want to cover the following topics in deformable grasping and manipulation. First, we want to talk about why we even need to use simulation when studying interactions with deformables. Then I'll show our work in DefGraspSim, which is a tool for simulating deformable grasps. Along with that, some comparison of simulated to real-world results. I'll then highlight some key shortcomings of FEM-based simulation, in particular speed and differentiability, and show how we're currently using deep neural networks to act as an alternative to FEM. Then we'll talk about work in deformable shape matching using DeformerNet. And so you can see these topics will be split into two groups. I'll be discussing the application of grasping, and then Alan will be covering DeformerNet for manipulation. Okay, so when we think of grasping 3D deformable objects, we as humans can have very different strategies based on the object and the task itself. For some examples, let's say we're picking up delicate fruits from a bush. In this case, we want to avoid grasping it such that it imparts too much deformation because this would bruise the fruit permanently and it wouldn't sell. And when we're grasping deformable containers, it's possible that you might crush its contents. For example, I would avoid grasping along the face of this Cheez-It box. But if the box were rigid and doesn't deform to my grasp, I could just grasp it any way I want. Another example is robotic surgery that includes manipulating soft tissues. We want to grasp the tissue in a way that will allow us to maneuver it in the way we want, for example, to stretch it or to perform processes like suturing. And lastly, sometimes the grasp just doesn't even matter. In fact, it's way easier to pick up this soft teddy bear than to pick up a rigid version of it, because a soft bear can deform to the gripper and actually improve contact. So it became clear to us when thinking about this topic that choosing best grasps for 3D deformable objects is object dependent and task dependent. And since these grasp goals are so diverse, we wanted a way to sort of evaluate grasp on a whole range of objects and therefore launch a full-scale simulation study. So this full-scale study is, we believe, best performed in simulation for many reasons. As we've heard a lot today, deformable objects have infinite degrees of freedom and are described by continuous field quantities such as deformation and stress fields. These quantities, more importantly, are basically impossible to measure in the real world and in real time, but this can be done in simulation. So simulation leads to safe experiments that are repeatable, resettable, and easily accessible, especially during a pandemic. So we present DefGraspSim, which enables automatic and systematic evaluation of grasp outcomes for grasps on general 3D deformable objects. Our contribution here is twofold. First, we release a new data set of 3D deformable objects, which is one of the largest in existence at 34 objects. Of course, this is tiny compared to the millions of rigid object models that are out there, but it's a good start, and we hope the community will also add to it. Secondly, we then use the NVIDIA Isaac GEM simulator that simulates deformable interactions using 3D FEM, the finite element method. And using this background, we create a code base that allows users to run GRASP experiments on any object of their choice. Let's look at that in a bit of detail next. And this is what using DefGraspSim looks like in practice. First, you can choose any object, either some from our existing data set or a custom model of your own. Then you can choose to run any of these GRASP experiments on that object and record the outcome of that GRASP. For example, some of these outcomes include the final stress field of that object after grasping, or the final deformation field. For example, maybe the total deformation that the shape undergoes during reorientation under gravity, or simply whether it was picked up or not. And so these different metrics can be chosen based on the object and whatever task you're interested in. Now, I want to mention that users can also design custom GRASP measures that they want to look at that might not be included from our code base, because at each time step, a full state tensor is actually made available to the user. This full state tensor includes full nodal positions and velocities, element stress tensors, as well as contact points and contact forces. And to our knowledge, this is the most complete per time step state tensor that there is out there for 3D deformable objects. So we're happy to see that this ability to design custom GRASP measures is starting to be used in the community already. For example, in this recent work by Lei et al. And his team in predicting GRASP success. Now, the next natural question to ask is, well, do these simulated experiments have good correspondence with the real world? To answer the question, we performed a few pilots into real studies where the material parameters we feed into our DefGraspSim simulator are only roughly estimated based on typical material values. So that's to say there's no fine tuning. Okay, so let's see some examples of estimating the stresses imparted on a piece of tofu during grasping. We see that there are qualitative similarities in shape when doing in the real world on the left versus in DefGraspSim on the right. As I mentioned before, you're able to actually extract the stress field of the object at every timestamp. And according to existing literature, we see that permanent breakage can happen at around 3,000 pascals. We then see some similarities between the stress fields predicted in DefGraspSim compared to what shows in real world. So for example, GRASP A didn't impart any breakage, but in simulation, we predict that GRASP B would, especially around the edges of the gripper. And indeed, that's what happens. And the third example of another grasp on this tofu is along its long axis, and these regions of high stress are shown in red. So we see that breakage indeed occurs along these areas. And even though we don't have the full, let's say, state tensor of this real piece of Trader Joe's tofu, we can see that the qualitative results are similar. We also have some experiments testing deformation of picking up a rubber tube, for example. And in our paper, we do have some additional experiments on stability as well as volume changes of bottles, if you would like to check that out. All right, so this tool is pretty promising and I believe useful, but there is one major shortcoming, and that is that it's slow because it does use a computationally intensive finite element method. So in fact, one of those GRASP tests can take as long as 5 minutes, especially if the object mesh is dense. For example, when you have very complicated geometries with features that you want to preserve. And so we were looking around for solutions, and we found an existing DeepMind paper that tried to solve this very same problem in 2020 by representing a physics simulator, an FEM-driven physics simulator, as a deep neural network. So I'm going to just give an overview of that work. I think it can be relevant to some of us. So this work, basically the key insight is that meshes are natural representations for structured objects, including 3D deformable objects. And therefore we should also represent objects as meshes for deep learning. In the past, objects have often been represented as point clouds, and popular machine learning methods that work on point clouds such as PointNet and PointNet++ have been very successful, but there is no inherent connectivity between points, unlike in FEM. So on the other hand, as opposed to point clouds, meshes are collections of connected vertices and edges that don't change over time, that clearly define the shape and structure of an object. And these meshes are the go-to representation for computing dynamics using numerical techniques. For example, in our DefGraspSim work, all deformable objects are indeed represented as meshes and not point clouds. Now, MeshGraphNets aims to solve the problem that we were facing, which is, that scientific simulations like FEM are expensive, so can we use mesh-based graph structures in machine learning to do predictions instead? And they found that the answer was yes. So they were able to train a one-time step prediction, where at each step, the physical system is represented as a graph. It's then encoded, processed, decoded, and then these output features can be used to directly calculate the next state of the system. And this is just rolled out over the course of a trajectory. So I will show an example of the power of this network in predicting the deformation and stress on a 3D plate when it comes in contact with an obstacle. So on the left is the ground truth generated by FEM, and on the right is prediction that DeepMind did using MeshGraphNets. So we wanted to actually modify this architecture for our application in 3D deformable grasping using a gripper. This would involve the use of grippers that are realistic to what we see in the real world rather than arbitrary obstacles. And the hope is to eventually use this as a grasp planning module. Okay, so I'm going to show some example results for how we've tailored this architecture for 3D deformable grasping, where the ground truth comes from our simulations in DefGraspSim. Specifically, when we're grasping 3D deformable objects, the most important quantities are stress and deformation fields. So that's what we are focusing on predicting. So we can get these quantities in ICRA as that full state tensor that I mentioned, but we want to see if we can get similar results using machine learning instead. Now, there are two main benefits of using this neural network. For one, it's much faster. A full rollout or a whole trajectory of squeezing the object until enough force is applied for safe pickup takes around 1 second using MeshGraphNets and 1 GPU. This takes maybe around 2 minutes using ICRA. So now, instead of doing grasp planning offline, where we would evaluate a bunch of candidate grasps first and then choose the best one, there's now potential to do this in an online manner. Secondly, neural networks are differentiable. Thus, we want to use it to actually optimize an initial grasp pose to produce the best grasp outcome, whether that be minimizing stress or maximizing deformation, whatever that might be for you. This sort of differentiable optimization is not something we can do in ICRA. Okay, so some examples of using MeshGraphNets for prediction are shown. This is an example applied to a grasping scenario where those two solid rectangular prisms are the two parallel jaw grippers. So in this visualization, we plot the nodes of the object's mesh, which in this case is a simple rectangular prism, just like the tofu. And on the left is the ground truth response of this object generated by DefGraspSim. You can see that as the gripper squeezes during the trajectory, the deformation increases, and so does the stress, where the nodes on the object are colored according to the stresses at that point. And on the right is the prediction that we generated, and you can see it's very similar. We also extend the application of MeshGraphNets to near rigid objects, for which we say that deformation is negligible. And this is motivated by real life grasping scenarios, because when you're grasping near rigid objects, we can't just command the gripper to close until some fixed distance. Because if they are quite rigid, that could actually damage the object and the grippers, right, if the object is stiff enough. In reality, force commands are more practical. That is, you can tell, or you would like to tell a robot to squeeze an object until a certain ideal total force is achieved, at which point then you can feel free to start picking up the object. So we changed also the network architecture to allow for kind of the external action to be the total gripper force instead of, let's say, change in gripper position. And as you can see, the resulting predictions for stress imparted on the object are very similar from the ground truth compared to after training. We also take advantage of the differentiability of this neural network. And here's one preliminary example, but we can start to use it to optimize or refine an initial grasp pose to a better one according to some metric. So in this particular example, we're trying to refine the grasp pose so that it maximizes the resulting stress of the object. So through this optimization process, the initial gripper pose is in blue, and it eventually becomes shifted up to a pose in orange that you can see ends up being localized around the edges of the prism, where because curvature discontinuities are higher there, this typically would actually lead to higher stresses. So in practice though, I think we rarely want to maximize stress on an object unless you're really trying to break tofu for some reason. Yeah, you probably would want to do the opposite, but this is a great example of what we hope to be able to do with the differentiability of the network. Okay, so that was for my part for grasping. I would love if you have any questions later on, you can feel free to contact me if you want to also get started with DefGraspSim. But now Alan will take over for manipulation.
Okay, awesome. You may recognize me from the acknowledgements slide earlier, which was going to be the extent of my involvement in this talk before last night. So Tucker couldn't make it, he had a flight that was canceled, but luckily I'm a collaborator on the project he was going to talk about. And much more importantly, my flight was not canceled. So here we are together. All right. A bit about me, I'm an assistant professor at the University of Utah in the Robotics Center, but more notably, before I was a computer scientist, I was a paramedic on an ambulance in a very busy 911 system. So this is my second career, and that kind of shapes my applications in these kinds of things. And so I'm extremely excited to talk to you today because one of the things that I'd like you to take from this is an application space for a lot of your methods and your techniques that's very important and that I am very passionate about. So we're in the middle of a pretty big crisis that you may not be aware of, and that is that there are not enough medical providers, and it's getting worse, much worse. And this is true of providers at all levels of healthcare. So from EMTs and paramedics in the pre-hospital setting to nurses, physicians, specialists, and surgeons. And the pandemic has made this much worse as well. So I'm going to talk about surgeons for a second. And specifically, if we look at cardiothoracic surgery, a pretty important branch of surgery, many would argue, the demand for these surgeons is going up. And that's because we're an aging and growing population, right? So many of us, there's more of us than there used to be. We're aging and we're becoming in need of these kind of specialized medical interventions, right? And because of specifics about the distribution of this aging population, the need for surgeons is actually growing at a rate greater than the population is. Here's the problem, though. The number of surgeons is not. The number of surgeons is in fact declining, and it's projected that by the year 2035-ish, the caseload per surgeon will more than double what it is today. This is an issue, right? Something that we need to address. So there are a lot of ways that this needs to be addressed. We need to create a healthier population. We need to make, we need to recruit more surgeons. We need to make their lives easier, but I don't care about any of that because I'm a computer scientist, right? And so, and a roboticist, I want to automate pieces of surgery, right? How hard could that possibly be? So I'm about to show you a video of surgery, robot-assisted surgery. If that bothers you, feel free to turn away and I'll tell you when it's over, okay? So here we have a video of a surgeon teleoperating a Da Vinci surgical robot to remove a lobe of a lung. And I want you to look at this video and think about the challenges that this specific application introduces to automation. So there's a bunch of them, right? One, we can look at the perception challenges, which are kind of unique to this space. Everything's kind of the same color, right? It's this gross gray pinkish color. Everything kind of looks pretty similar compared to at least when we think about manipulation in like industrial settings. And so that makes feature matching hard, increases the computer vision challenges. Everything's shiny, right? And so we have this specular effect that makes things difficult. Structured light doesn't work as well, for instance, right? We don't have a lot of data, right? Our data in medical robotics is frequently pathological in nature. That's a really funny joke. If you were a medical robotics audience, you'd be laughing a lot right now. We have pathological data, right? We don't have a lot of it. You can't collect it actively, right? Good luck signing somebody up to let you go poke around in their body just to train some model, right? These are the challenges. And so the ones that I specifically want to talk about today are the fact that we don't have a lot of data, or we can't get a lot of real world data, and everything's deformable, right? As you saw, almost all of this was deformable. If that focus surprises you, you're in the wrong place, or I'm in the wrong place, I guess, but either way. So let's talk about deformable object manipulation in the medical context. So before we can manipulate deformable objects, we have to represent them, right? And as we've heard over and over today, this is very difficult, right? These are infinite degrees of freedom things to describe in a true way. We have these high dimensional representations. We need to choose from among these. I told you that the vision challenge was very difficult. I'm going to pretend that other people have solved that, which is what I like to do. And we're going to get our geometry in the form of point clouds. Now, the good news is that a lot of the smart people working on perception in medical robotics are producing sensors that give us point clouds. And so this is kind of a natural way to start to think about sensors in medicine. Okay, so we're going to focus on point clouds in this work. So this is a paper that Tucker and I's student Bao is presenting later this week on Thursday, I think. And so just a plug to that, go talk to him in his poster session. It's going to be awesome. Okay, so we want to manipulate deformable objects in medicine. We want to do it in such a way that we're leveraging kind of the sensing modality that we're getting. And so let's think about it in this way. This is the kind of sub problem we're going to solve here. So the first thing is we're going to take our current shape of some deformable object in the form of a partial view point cloud. We're going to take some goal in the form of a point cloud. We're going to figure out where on this object to grasp it with some robot-assisted surgery device. And then we're going to, in our work, take a shape servoing approach to kind of incrementally move our current state in a point cloud representation of the deformable object to that goal point cloud. So how do we go about selecting this manipulation point? We've heard about some principled ways to think about this. And our future work is taking a much more complex approach to this, but we wanted to focus on the manipulation. And so in this work, the manipulation point selection is kind of a heuristic-based approach where we say, well, if you can match some key points between your starting pose and your goal, the intuition is the things that move more should be closer to where you grab them. It's a starting point. It seems like a reasonable place to start. That's where we went. So that's how we select our manipulation point. Now, how do we represent then the state of these deformable objects that we're getting from the point cloud in a way that we can then computationally reason over in this shape servoing way, right? And so that's the next piece of this. And so what we do is we embed this point cloud in some lower dimensional latent space here using a sequence of point conv layers in a neural network, right? And so this gives us a lower dimensional representation that simultaneously, because of the training process, encodes features that are relevant to both the shape, structure, and manipulation of these objects, but is low dimensional enough that we can reason about it. So using that, we kind of embed this in a shape servoing control loop at a high level. So we take our point cloud from a sensor, we run it through this model that we call the DeformerNet, And that gives us an incremental action for our robot to take, moves us a little bit closer in this latent space toward our goal shape that we want, and we repeat this process. And so here's what the full model looks like. We have our feature extraction that we just talked about a little bit, that we get our current state from, as well as our goal state. So we embed these into the same latent space and look at the difference. And then we have another model or another piece of the same model that takes that difference and has learned how to manipulate the gripper of the object in order to move the robot such that the deformable object moves a little bit closer to where we're trying to go from a deformable object perspective. So how do we overcome this fact that we don't actually have the ability to get a lot of data from people, right, when we're deforming people, which is really deforming? So we're leveraging large-scale simulation to take steps toward that. And so this is what it looks like right now. We've got a simulated surgical robot over there on the right. This is an older version of that robot that you saw from the video. And we are placing in front of it in Isaac Gym a diverse set of shapes with different geometries, sizes, and stiffness properties, and letting it, in the way you all do, wiggle it around, right, for a while in simulation. And then from this, we get our training data that we train our method with. And so I encourage you to go talk to Bao to get the actual specifics on the results, but it works really well. So here we have objects that were not seen in the training being manipulated to goal shapes that were not seen during the training, obviously on a bunch of different geometries. So this is it working well in simulation, but how does it work well in the real world? And so it turns out that at least the ways that we've tested it, it works really well in the real world without us having to have done any kind of fine tuning or other changing of the method to get it to work in the real world. So here we have a robot that's not in the scene manipulating a laparoscopic tool that is in the scene that is grabbing this piece of foam. And here it is using our method manipulating the object, which is this goal point cloud that you see in red here. So in addition to that work, and this is now beyond the work that we're presenting at this conference into kind of some of the next steps that we've begun to take, we're also looking at bimanual manipulation for these as well. So the question you should be asking me is, how in the world are we going to get a goal point cloud in a real setting from like a surgeon that's trying to use this to help them, right? That's an excellent question. I'm glad I brought it up. So that's the key here, right? There's a lot of advantages to having this reasoning about the current state and the goal state kind of in this same modality that we're leveraging right now, but it does present this challenge, right? And so one of the things that we're taking steps toward is, well, if on a task-specific basis, you can come up with a low burden way for a non-expert human user to specify some parameter that can then be easily translated into a goal point cloud. You can create that small task-specific piece and then leverage our method on the back end that's not task-specific to accomplish a lot of things. And so that's where we're going with this, at least in the kind of near term, right? And so the first thing that we've seen to make this work is let's have a human define a plane. Now, there are other ways to get a robot to move a deformable thing to the other side of a plane, but the point here is that this is just one instantiation of this kind of interface translation layer, right? And so here we have a plane, and we have kind of a method that transforms the current point cloud into some point cloud that looks like what the object would look like on the other side of the plane in some way, and it's capable of using our method that reasons about the sequence of point clouds in a goal point cloud in order to get there. And this works both in simulation and on the real robot. And the medical application here is something called retraction, where we're thinking about moving a piece of tissue aside so that a human surgeon can then do the complicated pieces to whatever's underneath it, or visualize what's underneath of things like this, right? This is a common task in robotic surgery. So this isn't the only thing we're thinking about. We're also thinking about the task of anastomosis, which is connecting two tubes together, and how would a human specify what this connection should look like? here we've we're taking the approach where a human could specify a space curve that they want the two tubes to kind of look like when they're joined. And here we kind of swell that curve into a point cloud. That curve could be gathered from a 3D mouse or from the actual robotic device that they're using in surgery, kind of trace this curve in space where there are not tubes, and then have the method kind of join the tubes there, right? We're also looking at wrapping tissue around other objects, for instance, like in-stent placement and things like this. And so here, all of these are the same method underlying it, right? This point cloud reasoning shape servoing. This is just 3 instantiations of like heuristic ways that we've used more human, low burden ways to kind of specify goal representations that we then translate into this point cloud goal, right? Anyway, please work on medicine. It's all deformable. It's all super important. Come talk to me, talk to Tucker if you're interested. If you want a medical slant on things, let me know. So that I think is it for us, right? Awesome.
Thank you, Isabella and Darren. And thanks a lot also.
Please line up by the microphone or ask online.
Great. So first of all, fantastic talk. I honestly have a lot of questions, so I don't want to take up too much of time. We have to discuss them later.
There's more time.
Okay, but so
Later, I mean, not now.
So first for the GraspSim stuff. So 2 questions for that. There's been a growing amount of interest in using compliant and soft grippers. In the work that you've presented right now, are you assuming a rigid morphology, or are you assuming a very specific morphology that doesn't get any rigid morphology? Are you assuming a parallel jaw grip? Yeah.
So the question for DefGraspSim is, can this basically support compliant grippers? And also, am I assuming that the grippers are rigid and also of a specific geometry? Currently, ICRA does not support soft body to soft body interactions. But there has been existing work using ICRA where the grippers do have a compliant pad, but the objects are rigid. But you can't really have it both ways right now. That may change soon. And the parallel jaw gripper that I'm using is, it's kind of stripped of all defining features. It's loosely based on the panda hand, but it doesn't look exactly like that. And the reason for that is to, just like represent a general parallel jaw gripper. And this can definitely be tailored to other hands as well. You can upload different like URDF files to describe whatever hands you may want. So that might even include like multi-fingered hands if you'd like. Yeah.
The other question was, so first of all, thank you for moving away from SGM. I really don't like SGM, and I don't like it either.
I didn't say I don't like it.
Okay, but so in sort of this, using going down the deformation path, one of the concerns I always have with those kind of methods is what happens to things that are not in the source data set. Did you find that to be very much a problem in the kind of objects you're working with? And if so, or if not, just want to hear a little bit about that.
Okay, so the question is generally about generalization of deep neural networks and whether like my results would apply to maybe objects that I didn't see during training. Yeah, definitely. I think with a broad enough class of training objects, you should expect some generalization to those that do have similar features. I haven't tested the bounds of exactly how different objects can be, yet still generalized, but I think that is a challenging question and an open question in many ways. Right now, we're sticking to maybe like more simple geometric objects first, just to scope it out. We do see generalization from prisms to other shapes of prisms, but what about curved edges or shells, in fact? So I think as long as you have enough objects of each of these categories of geometries, then the hope is that you will see some generalization.
Wait, I think we have one question online, so I want to make sure that we're able to get to the online question.
Yeah, so the question online is, does the ICRA simulate simulation actually simulates the rigid gripper grasping, or does it use fixed points, anchor points?
Do I have to repeat that or no?
So you understand.
Okay. It does not use fixed points to get there. It actually does simulate the dynamics of the rigid gripper. So you would have to define like the inertial properties of every link in the URDF, for example. And it can also do built-in, for example, position control, velocity control, torque control. So in that sense, it is a robotic simulator because you can do control of the actuator.
Thank you. Let's do one more question because we are a bit running out
Yeah,
of
sorry, let's take one more question just because we have to get to the next speaker. So.
But Alan and Isabella is around.
Yeah, we'll be around.
Question for the professor. I was wondering, previous work on medical robotics basically looked at different flavors of CPD, 4-point trims with different regularizations, basically non-rigid registrations. And your work has not looked at that. So I was wondering, like, what advantages you have? You're probably much faster, but how accurate you are versus them, stuff like that.
Yeah, so I think that that's tackling a related but a little bit different, distinct problem, right? And so in the registration front, we're really looking at, well, I have some existing model of the anatomy. I want to deform it such that it's like what I'm looking at, and then that allows me to reason about the knowledge I had in the medical imaging, for instance, to then make decisions based on what I see. So we're just moving things, right? The things that are under the surface that we would then access, that we need to have that registration from the imaging for, we're not there yet. But once we start doing so, hugely important, absolutely.
Thank you so much.
Yep.
Well, thanks again.